Okay, in this video, we're going to talk about polynomial functions. A huge part of chapter 4 is related to polynomials, and so we definitely need to know what a polynomial is. Definition: a power function of degree n, where n is a natural number, is a function of the form f of x equals a times x to the n, where a is a real number and a is not 0. Okay, so f of x equals x squared and g of x equals x to the fourth. Okay, let's graph that. So f of x equals x squared, we've already got drawn there, and we've worked with that several times all over the place in chapter 3. We did things with parabolas. When x is 0, g is 0. When x is 1, g is 1. When x is negative 1, g is 1. Okay, so those 3 points are going to be on the graph of g. When x is 2, 2 to the fourth is 16. Okay, so 2, 16, way up there. When x is negative 2 to the fourth is 16, way up here. When x is 1 half to the fourth is 1 over 16. Okay, so here's 1 half, 1 over 16, and negative 1 half, 1 over 16. Okay, and so this is a graph that we get for g of x. When n is even, x sub n is always symmetric to the y-axis, and the points 0, 0, 1, 1, and negative 1, 1 are always on the graph. That's what I've got going on here. When x is greater than 1 or less than 1, the graph becomes more vertical. Okay, and that's what I see. For x being between 1 and negative 1, the graph becomes more flattened and closer to the x-axis. Okay. So of course it would look different if I were to graph like x to the 20th. Okay. I'd have something that's more vertical like, and something that's more closer to the x-axis, like in between 1 and negative 1. Next, f of x equal x cubed and g of x equal x to the fifth. Okay, so I've got x cubed graph. Here's 1, 1, 0, 0, and negative 1, 1 on the graph. Okay, when x is 0, and I'm going to graph g is 0. When x is 1, 1 to the fifth is 1. When x is negative 1 to the fifth is negative 1. Okay, so those 3 points are going to be on the graph of g. When x is 2, 2 to the fifth is 32. Okay, so 232 is way up there. Not on the scale that I've got there, but still on the graph. When x is negative 2 to the fifth is negative 32. Okay, so here's negative 32. When x is 1 half to the fifth is 1 over 32. Okay, so that's right about there. When x is negative 1 half, negative 1 over 32. Okay. When n is odd, x sub n is x to the n is always symmetric to the origin, and the points 0, 0, 1, 1, and negative 1, 1 are always on the graph. At least that's what I see here. Okay. When x is greater than 1 or x is less than 1, the graph becomes more vertical. And for x less than 1 or less than negative 1 or less than or greater than negative 1 and less than 1, the graph becomes more flat and closer to the x-axis. So that's what I see here in the case of g of x equal x to the fifth. I see in between 1 and negative 1 that the graph becomes more flattened, and I get more closer to the x-axis there. On the outside, if I'm greater than 1 or less than negative 1, I'm more vertical. So let's graph f of x equals 1 minus x to the fifth. Here's y equals x to the fifth. Okay, very much like y equal x cubed. Okay, just like y equal x to the fourth, looks very much like y equal x squared. Okay, y equal negative x to the fifth means that I reflect this about the y-axis. Okay, and then y equal negative x to the fifth plus 1 means that I'd shift up 1 unit. Okay. Another example, f of x equals 1/2 times x minus 1 to the fourth. Okay, well, x to the fourth, I've already graphed before. Here's the graph of y equal x to the fourth. Y equal 1/2 times x to the fourth. 1/2 means that I'd have a vertical stretch of the vertical shrink of the original graph. Okay, so 0, 0 is on the graph. 1, 1/2 is on the graph. Negative 1, 1/2 is on the graph. Let's see. If x is 2, y would be negative 8 or 8. Okay, 8 is right here. And when x is negative 2, y would be 8. Okay, 8 is up here. Okay, y equals 1/2 times the quantity x minus 1 to the fourth. I would shift this graph to the right 1 unit with all the points. And so 1, 0 would be on the graph, 2, 1/2 would be on the graph, and 0, 1/2 would be on the graph. Okay. Definition, a polynomial function of degree n, where n is a whole number, is a function of the form f of x equals a sub n times x to the n plus a sub n times a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 plus etc. Plus a sub 1 times x to the first plus a sub 0, where a sub n minus 1, a sub n minus 2, etc., all the way down to a sub 1 and a sub 0, those are real numbers. Okay, the domain of any polynomial function is all real numbers. Okay, there's no division by anything, and there's no square roots or any other radicals that I got to worry about. So all real numbers. The degree is the largest power of x that appears. Okay, so the degree is important. If f of x equals 0, we say f has no degree to it. Okay, so we'll look at that. Here's some examples. F of x equals 3 times x minus 3, 3 plus x cubed minus 8x to the fourth. This would be a polynomial of degree 4. 4 is the highest power of x that I see. Okay. Also, this is a polynomial because the two conditions for being a polynomial are satisfied. Condition 1 says that every single coefficient is a real number. 3, 1, and negative 8, those are real numbers, so I'm not doing anything with imaginary numbers. Okay. And condition 2, says that every single power of x is a whole number. 3 and 4, those are whole numbers. A whole number is a number that is 0 or greater, and also a counting number. Okay, g of x equals the square root of x. That's not a polynomial because the square root of x can be written as x to the 1/2 power, and 1/2 is not a whole number, so end of story, not a polynomial. Okay, if we have h of x equals x squared minus 4 divided by x plus 2, the numerator is going to factor nicely for me as x minus 2 times x plus 2 divided by x plus 2. The x plus 2's will cancel, leaving me with x minus 2. So this is a polynomial of degree 1. 1 is the largest power of x that I see, and this is a polynomial. Okay. If I have f of x equal x squared minus 4 divided by x cubed plus 1, both the numerator and denominator will factor nicely for me. But I don't think that much matters because I still won't have a polynomial when all is said and done, because I'll still be dividing by x cubed plus 1. Okay. In other words, nothing's going to cancel there. K of x equals 0 is a polynomial that has no degree. Okay, let me talk about the no degree part after we look at this next example. F of x equals 8 is a polynomial of degree 0. So 8 is a real number, x to the 0, 0 is a whole number. Okay, that's why I have a degree 0 polynomial. Now, why isn't this one a polynomial of degree 0 also? K of x. Well, 0 is the same as 0 times x squared. 0 is the same as 0 times x cubed. 0 is the same as 0 times x to the 43rd. 0 times anything is 0. Okay, so I can let the highest power of x be any number I want. And that wouldn't be right. So the 0 polynomial function is the only polynomial that we say has no degree to it. Okay, if we have f of x equal 8, for example, 8 is a polynomial. 8 is the same thing times x times 8 times x to the 0. Okay, x to the 0 is 1, so 8 times 1 is 1. And that's a polynomial. The degree is 0. Okay, since x to the 0 power is represented there. G of x equals negative 3x times x plus 2 to the 12th. So I got negative 3x times x squared plus 4x plus 4. Okay, and there should be an x right there. Negative 3x times x squared plus 4x plus 4. When I distribute the negative 3x, I get negative 3x cubed minus should be minus 12x. Minus 12. Okay, minus 12x. So this is a polynomial of degree 3. 3 is the largest power of x that I see there. And the point of that, now we're going to see this a lot, but the point of this one is to say that, we have a polynomial, it's just not written in polynomial form. Okay, it's not written in the form up here where we've got, everything's expanded out, and we don't see that in this case. But this is a degree 3 polynomial. Okay, h of x is the absolute value of the square root of x plus 2. This is not a polynomial because the very easy answer would be to say that I don't have anything involving absolute value bars in the original function. You see the absolute value of x plus 2, that's the same as x plus 2 if x plus 2 is greater than or equal to 0, and negative x plus 2 if x plus 2 is negative. Okay, so I'm going to get two different integer values there for x plus 2 because of how that's defined as a piecewise function, not a polynomial. Okay. Definition: if f is a polynomial function and r is a number for which f of r is equal to 0, then r is called a 0 of f, or sometimes we say a root of f. This book uses 0. If r is a 0 of f, then x minus r is a factor of f. Okay. For example, check if r equals 0 and r equals 2 and r equals negative 5 are zeros of the polynomial function f of x equal x cubed plus x squared minus 17x plus 15. Okay, well I would just plug in the two numbers. That's what a root is. I plug it in and I get 0 in return. So f of 2 cubed is 8, plus 4 is 12, minus 34 is negative 22, plus 15 gives me negative 7 as the output. And I'm looking for an output of 0, not any other number. So no, so 2 is not a 0 of f. How about negative 5? Negative 5 cubed is negative 125, plus 25 gives me negative 100. Okay, minus 17 times negative 5, that's 85. So I got negative 15, plus 15 gives me 0. Okay, since I have a number that returns 0 when I plug that into the function, then yeah, that number is a 0 of f. So the factor x minus negative 5 or x plus 5 is a factor of f. Okay, I can also conclude that x minus 2 is not a factor because I did not get 0 in return. Okay, why don't we stop right there?